Hey everyone, let's dive right into this explainer. Today, we're taking a fascinating spatial tour through the multi-layered digital fortress that is the embedded Linux kernel. If you've ever stopped and wondered how your modern smart devices just run, like how they manage to stay so incredibly reliable without crashing the whole system every single time a random app glitches out, well, you are absolutely in the right place. We're going to break down the exact spatial models, the memory protections, and the execution layers that make all of this possible.
Here's our architectural blueprint for the journey. We'll start with the embedded paradigm shift, then look at our foundation, which is the hardware abstraction layer. After that, we'll hit the core kernel subsystems, explore memory and process scheduling, cross the system call boundary, and finally trace a vertical execution right through the whole stack.
So Part 1, the embedded paradigm shift, or leaving the flatlands.
To really appreciate why modern embedded Linux systems are built like these impenetrable multi-layered fortresses, we've kind of got to look back at the fragile environments we left behind. Think about legacy embedded systems running traditional real-time operating systems, or RTOS. Back then, memory was seriously expensive, so literally everything was compiled into just one tightly controlled flat software image. The glaring issue there? A single, tiny app crash could take down the entire physical machine. Why? Because there was absolutely zero isolation. But as memory got cheaper, software became the real differentiator. So embedded Linux brought in this massive structural paradigm shift based entirely on strict fault isolation and modularity. An app can completely crash and burn, but the system survives.
And this structural separation is brilliant. We are moving away from that legacy flat model, where apps and drivers are all jumbled together in one super dangerous shared space, over to the monolithic Linux model. We get the strict physical dividing line separating the unprivileged user space, which is where your apps live, from the privileged kernel space, where the critical drivers and network stacks do their thing. This virtual address-based separation is basically the secret sauce of modern embedded stability.
All right, moving to Part 2, foundation, the hardware abstraction layer, or taming the wild.
Now that we have the big picture, let's get down to the absolute bottom layer of our fortress to see exactly how Linux tames raw, chaotic electronics. At the very base of everything is the hardware abstraction layer, or the how. Look, in the embedded world, processors don't just come in one flavor, right? You've got ARM, MIPS, PowerPC, Super H, it's a jungle. The how acts as the ultimate universal translator. It takes all those wildly different hardware signals, things like memory map setups, DMA, exception handling, and it completely translates them into a standardized language that the universal Linux kernel sitting right above it can actually understand.
So the big takeaway here is that by abstracting the hardware, developers can write a device driver just one time and then seamlessly port that software across completely different physical boards. It totally replaces the older, super rigid board support package concept with something that virtualizes the hardware platform from the ground up. It's a real game changer. Which brings us to Part 3, the core kernel subsystems. Welcome to the engine room.
Moving just one level up from the hail, we enter the beating heart of the system. I love calling this the engine room. Here you have 5 core subsystems working in absolute perfect harmony. You've got the memory manager handing out virtual memory to apps, the I/O subsystem giving us uniform interfaces for devices, the networking stack handling everything from Bluetooth to TCP/IP, the scheduler managing all the multitasking, and of course, the virtual file system.
And honestly, it is amazing how much heavy lifting components like the VFS actually do to hide the incredibly messy physical details of storage. It doesn't matter if your data is sitting on an ext2 flash drive, some compressed CramFest, or a temporary RAMFS. The VFS just provides one smooth, consistent directory structure. Apps can just read and write their files without ever having to sweat the complicated physics of the actual storage medium.
Plus, because our applications are securely locked in their own isolated rooms up in user space, we desperately need a highly secure mail system to let them talk to each other. Enter the Inter-Process Communication, or IPC, subsystem. This provides really strict, tightly controlled mechanisms, things like signals, pipes, and sockets. That way, isolated processes can safely swap data without ever breaching the thick protective walls of their sandboxes.
Part 4, memory and process scheduling. Let's look at creating those safe zones.
Let's break down how the kernel actually builds those safe rooms. Now, the Linux scheduler is constantly juggling tasks, right? But the key is understanding the difference in containment here. Processes are entirely independent entities. They have completely separate address spaces, and they only ever interact through that IPC mail system we just talked about. Threads, on the other hand, are just subsets of a process, so they happily share the exact same memory space, the text, the data, the heap, all inside that one single process. For the processes themselves, that walled-off isolation is pulled off through the sheer magic of virtual memory. Every single process gets its own perfect illusion of space, stretching from the compiled code at the bottom all the way up to the dynamically growing heap and stack at the top. Because memory is neatly chopped up into 4 kilobyte pages and managed virtually, if an application crashes, it literally just causes a simple segmentation fault inside its own little bubble. It is completely prevented from corrupting the kernel or crashing any other app.
But wait a second. This brings up a massive architectural challenge. If every single application is permanently trapped inside its own invisible wall of virtual memory, how in the world do we ever interact with the outside world? An app is physically blocked from touching the hardware. It can't read a file directly, it can't send a network packet, it can't even print to the screen. So how does anything actually get done?
Part 5. Crossing the boundary, the system call. To solve this massive isolation problem, the architecture relies on hardware-enforced gateways. Let's walk through exactly how this works. When a sandboxed user app actually needs a hardware service, let's say reading a file, it cannot just reach out and grab it. No way. Instead, it deliberately triggers a hardware exception. This essentially forces the CPU to pause, elevate its own privileges, and securely switch into kernel mode through a tightly controlled, highly specific gateway called the system call interface.
Think of it exactly like slipping a request note under a locked, bulletproof door to a highly trusted guard. The application makes the request, but it never, ever touches the hardware itself. Only the highly privileged kernel gets to actually touch the physical storage or network interface to execute that dangerous hardware action. And then, once it's done, the result is securely passed right back up to the application.
Part 6. The vertical execution trace, where we tie it all together.
For our grand finale here, let's watch all of these architectural layers fire off in rapid sequence. When you tell an app to do something super basic, like printing text to a screen, it is not just one simple action. That data literally plummets vertically down through 5 distinct, fully isolated layers of our embedded fortress.
Starting way up at the top of the user space, an app calls a function like printf for hello world, which lives inside a dynamically linked shared library. That library takes the request, wraps it up into a precise system call, and drops it straight across the protection boundary into the kernel space. The kernel's I/O subsystem and character device drivers take over from there, routing it down to the hardware abstraction layer, which translates that driver command into the exact electrical pulses needed to light up the physical console.
Every layer perfectly isolated, every interaction strictly controlled. The architecture of modern embedded stability. This trace perfectly summarizes why the embedded Linux architecture is just so incredibly robust. It doesn't cross its fingers and hope a flat software image won't crash. It actively relies on spatial isolation, dynamic memory protection, and strictly controlled boundaries at every single level of execution.
So, knowing how this invisible, layered fortress actually operates under the hood, how might it change the way you look at the smart devices sitting right next to you? Next time your smart thermostat clicks on, or your router processes a Wi-Fi packet, or your smartwatch updates its display, don't just see a piece of plastic and glass. Imagine that high-speed vertical trace plunging from an isolated user sandbox, securely crossing the system call boundary, processing through the engine room, and hitting the raw hardware, thousands and thousands of times a second, absolutely flawlessly. Thanks for joining me on this explainer, and keep exploring the incredible architecture running the world around you.